Hello YouTube RJ. Today's video is going to be a continuation of our ham radio project. We already built the broadcast filter in previous videos, and today we're going to start on our crystal filter. Now there's no reason to be afraid of a crystal filter. There seems like it's magic and there's all this difficult math and such involved, and there's really not. I'm going to show you a very easy way to design a crystal filter for a radio. But they are an important part of the component of the radio. It's good to understand how they work and how to make a good efficient one, because it can make or break your radio. A lot of questions have been sent and a few comments have been put in the YouTube video. I've got a couple emails asking, hey, what kind of radio are you building? You haven't told us what frequencies it's going to work on and such. Well, it's an HF radio, and I think what we're going to do is we're going to start out making an 80 meter radio. And before you get disappointed that we're doing just 80 meters, this is going to be a modular build where we build a radio one step at a time, build the modules up, get it working on 80 meters, and then look at what can we do to make this thing a multi-band transceiver that would be useful on your radio bench that you would be proud to use. We're going to go through, obviously the broadcast filter, doesn't matter what band you're going to use. Crystal filters, there is some things to think about when you're deciding what bands to use, but that's kind of why I use the frequency I use, is because it's a frequency that we can make work on 80 through 10 meters. So that's going to work to our advantage later on as we add bands and decide to go with a multi-band radio. Hope you find it interesting. Hope you'll hang in there with me through this project. So let's get into designing our own crystal filters. We're going to move ahead on our crystal filter designing. In the last video, we built the G3UUR oscillator here, and we went over the functions of it. And now I've actually went through and simply inserted around 100 crystals in with it connected to the frequency meter. What I did was I sorted them, put out a piece of paper, wrote values, sorted them into groups. I've got 6 of them here that are very close together. They're all within, say, 50 hertz or so. These are the 6 I've decided I'm going to use for our crystal filter, or one side of our crystal filter. I wanted to quickly take you through how I use this and into the software we work with and how we actually design the crystal filter. So the first thing is, I got a piece of paper here. I've magic markered a number on the 6 crystals. And I've set up a little chart here that I'll be moving over into Excel. First thing I did was take my LCR meter, calibrate it, and then measure each of them. And they came out surprisingly close. They were bouncing around just a little bit around 4.3 picofarad. And so I ended up deciding they were all so bouncing around and so close. I went ahead with 4.3 on them all. They seem to be that close. Then I went through and started doing the frequency, which I'll show you in just a moment. Put the crystal in, forget to push the button, write the wrong value down, realize it, scratch it out. Hey, I make mistakes. I'm no expert. Push the button to get F and write in what you get. Release the button. Now give a few seconds for it to settle. Plug it in, give it a few seconds to settle down. Write down what you've got with the button pushed. Let go of the button, give it a few seconds to settle in, write down what you end up with for FC. Now, CS is the capacitor over here that we have the CS capacitor on it, and I got 48, if you can't read it, it's 0.6 right there. It's 48.6 picofarad, measured accurately with my LCR meter. And so they all, of course, that capacitance is applied to all of them. I saved crystal 6 to do with you. So I'm going to pull crystal 5 out. I'm going to put crystal 6 in the holder, push the button. I'm going to give it a little bit of time to settle. And then I'm going to, I know it's going to come out to be 11.055. None of them are that far apart. 432 is what I get. So 4, 3, 2. Now I'm going to release the button. I'm going to give it a couple seconds to settle on. And I know it's going to be 11.057. And I'm looking at 238. So 238. So you can see how close all of these are. So very close to each other. That's what you're looking for. So now we've got our information on our crystal. We're done with this for the moment. Actually, I have another set of crystals to lay out, because you're going to see the crystal filter I'm going to build is two-sided. It's CW and SSB. So I'm going to do another set of crystals. It'll be done exactly the same way, but let's take these and let me kick over the computer and I'll show you exactly how we take this information and we design a crystal filter. So I took all the information that we charted down about the 6 crystals we're working with, and I plugged them into an Excel spreadsheet and created averages for the frequencies for their holder capacitance, which were all the same, so that was easy. And then what I'm doing here is I'm showing a program called Dishel 2052. There's an older version out there too. I think it's 203. I'll put a link to where to get this one. This is a little newer version of the program. We're going to use that, and what we're going to do is we're going to punch our information in. We're going to take those numbers and we're going to use them in this program. And what we're going to do is we're going to open this program and run the exe. I'll close this folder down and bring this over. Once you unzip it, you get that folder and you just go in the exe and run it. So this is Dishel. And the way Dishel works is you use your motional perimeters, just one of them. You can use either one you want to use. The series frequency, the holder capacitance, how wide the 3 dB you want, bandwidth of the filter, how much ripple you're willing to put up with, how many crystals you're going to use, and then of course this controls how far this display spans, okay? So what we're going to do is we're going to take and we're going to use the information we got to figure out what we're going to do. And we're going to build, instead of building where this particular design is building a different type of filter than we're going to build. Chebyshev, we'll give it a try. Chebyshev filter, very common filter. You have different capacitors used in that design. We're going to do a simpler cone filter, which uses all the same size capacitors. Very common filter in HF, home DIY stuff. So we're going to use that. And how we're going to come up with the information to create that is, I'm going to go ahead and fill out a couple of things. One is our motional capacitance, okay? But I've got to come up with this number. We don't have the calculations done. So the first thing we're going to do is go to Crystal G3UUR method. And that's going to give us another little pop-up. And this little pop-up, I'll move this one over here. I guess I can't. We'll work with it right there. So what we're going to do is we're going to fill out some things. You probably recognize this. This is the G3UUR oscillator that we did all our stuff on. We're going to go in here, and what we're going to do is, this is switch close. Switch close is what we call F. So we're going to put in the average. And the average for our 6 crystals was 11,055.485. It's in kilohertz. So you got to remember, your last digits are going to be behind a decimal point. So the switch open we call FC. That's where we have the frequency when the capacitor is in series. That's going to be 11,057,259. This is why I put it in these numbers in a spreadsheet, just to generate the average for me. Oops, forgot my decimal point. 0.259. See, I almost forgot. That's why I told you that. So now we've got this in. Okay, what was our holder capacitance? Well, it was 4.3. The CS, the capacitor on our circuit, measures, in my case, 48.6. That would be different for you. And once we do this, we can calculate. Now, when we calculate, we get a couple things down here. We get the motional inductance and the motional capacitance, and we get the crystal series frequency. So this is the information we want. So we need to write down, in my case, I'm going to write down the CM, 17.581. I'm going to write down my series frequency. So once I've got that wrote down, and I've got it, I can close this window. This is what we wanted right here. Close that, go to cone, and we get another pop-up that we get to fill in. Okay, what was our motional capacitance? It was 17.581. What was our series frequency? It was 11,055.079. How wide a filter do we want? Well, I'm building a 2.7 kilohertz. How many crystals? We're going to use 6. What was my holder capacitance? It was 4.3. And now if I hit calculate, I'm going to come down here and see this is what the filter's frequency is expected to be. This is the capacitance of the capacitors in our cone filter. They're all the same. And this is what we can expect to be the in and output impedance of this filter, 129.8, so basically 130 ohms. So what we want to do is we want to write all this down, and we will use this to build our filter. We can close this. Now, if you want to play with this, we can calculate this, and if you were to build this type of filter, this is what you would see. Now, first of all, I would change that ripple to something more realistic. And let's put our, you don't want 1 dB of ripple unless you have to have it. I mean, unless you can't get better than that. Let's put in our 2.7 here. Let's put our 4.3 in here. Let's put our frequency in, 11055.079. And our CM was 17.581. And this will just give you kind of a visual representation of kind of what the filter should act like. Now, our cone filter won't be exactly this, but it'll be pretty close actually. So you can see what kind of skirts you have. You have a little bit of a looser skirt on the low frequency side than you do the high frequency side, not uncommon. If you were to design this, you can see there's some difference. One is the impedance would be 147, a little different. And then what would happen is you would design it using these different capacitance. We're not doing that. Ours is a lot simpler to do. So let's bail out of this and let's go design this thing in the real world based on the numbers we came out of and see how we come out. Okay, so what I've done is I've created a little prototype board here, as you can see, using the QRP-Me little Me squares. Just super glue them onto a circuit board, laid them out to where they gave me. And this circuit is just a cone filter. I'll put a schematic up on the screen here to show you. It's just your crystals in series, and they're parallel off by capacitive. And of course, it's coupled at the end with some capacitors. And then we'll come back to the transformers in a minute. But this creates a cone filter that, you know, typically you use a single capacitor, all the same capacitors. And the capacitors control the bandwidth of your crystal filter. I just took a guess and started out at 100 picofarad, popped it in. Then it was too narrow. I think I was down around 2.5 kilohertz. I backed up and paralleled the 68s with 22 picofarads. And that's where we are now. And as you might be able to see on the screen here, I've got a screen capture I can show. That pretty well nailed it. It's the 3 dB bandwidth is running just about 2.7 kilohertz, 2.7, 2.733 sometimes, but right there at that 2.7 kilohertz bandwidth. So I'm very happy with that. And then the problem then was, of course, in matching impedance. And before I created these transformers, my losses were pretty good. They were around 6 dB. They weren't horrible. They were around 6 dB. But I felt like it should be better. And I thought I should be able to, you know, looking at other crystal filters. And so, you know, we want to get it right. But I had hoped that the impedance, matching the impedance would help there. So I decided to go at it 2 different ways. The first way was we brought in the Nano VNA. I grabbed my Nano VNA and I connected it up and took a look at it from a point of view of what the input impedance was. And it was coming out in the neighborhood of about 134 ohms, which is about right. Typically these come out somewhere between 100 and 200 from my understanding. You know, bear in mind, I'm not an expert. I got a hair there. It's driving me crazy. We can't have my hair in the circuits. So, you know, I'm not an expert, but from what I could read, that's about what we're looking for. That's the impedance you're normally going to see. So then I thought, okay, well, we need to design these transformers and build them to match the impedance. But I got curious about something. Charlie Morris had a technique that he used one time on one of his videos. He might have done it multiple times, but I seen him do it once, where he took and he figured out what the impedance was by hooking two pots in series, without the transformers obviously, in series. And then what he did is he tweaked them for the absolute flattest bandpass he could get, the least amount of ripple. You might notice the ripple's really good. I mean, it's really good on this filter. The ripple wasn't bad before I even started this, but I was able to get it better by tweaking them. Now the thing is, you don't want to have a lot of resistance on one and no resistance on the other. So what I did is I started out with them 0 ohms both, and I would turn, you know, 1/8 of a turn on this one and 1/8 of a turn on that one and see what I got. And then I'd go 1/4 and then 1/4, keep them matched and see, is it better, is it worse? And I played with it a little until I got a little bit of improvement. And then I couldn't get any more. Now while I'm doing this, the losses are going up dramatically. Don't worry about that. Obviously, we're putting resistance in the line, you're going to get losses. So anyway, I've got it to the least amount of resistance, the least amount of loss that gave me the best bandpass, least amount of ripple, just the way Charlie showed it. And then, of course, I quickly desoldered these and took them off and measured them. And to my surprise, the Nano VNA said it was 134 ohms. These were, you know, a few ohms apart, but the average of them was 136 ohms. So that was just a verification cross check of this technique compared to the VNA, and I was literally shocked at how close they actually came out. It was, I could have fell off the chair. I couldn't believe how close. I would have expected it to be in the ballpark, maybe 15 ohms, 20 ohms one way or another. No, they were very close, within 2 ohms. So based on that, I went ahead with that as my impedance. And what I did was I used a little spreadsheet. I'll pop it up here. Okay, as you can see the spreadsheet. The spreadsheet, what it does is you can see you punch in the resistance that you have. And then what it does is it calculates out what you really need. Charlie Morris's procedure was you get the resistance from here and you add 50. This is what the spreadsheet does. It adds 50. And it calculates the squares of these to come up with a ratio. And it gives me a ratio. And then over here, you notice I've got a number of windings that I'm showing. And these number of windings that I'm showing, it calculates out and tells me what the matching winding would be. It's just multiplying 5 windings by this ratio to come up with this is where you would be with 5 windings. How many windings you would need on a secondary. You can't wind a partial winding, obviously, so you go down the list and you find the closest match to an integer as you can get. And you see here I ended up with, at 12 windings, ended up with 23. And you notice very little left. So 12 to 23 is in, you know, it's more windings than I like, but that's what I went with. And so basically I wound the two toroids, FT3743s, and I used a, you know, a basic colored, rust colored winding. And I used green winding, and that way when you get done you can figure out, you know, because you wind these things with the same color wire, you will pull your hair out because you'll get them confused and hooked up and can't figure out why things aren't working. And so basically I like to use multicolor. So when I get to the end, I know which windings won't, you know, the primary, which one's the secondary. And so then what I did was, in place of where the resistors were in series, I plopped these transformers in. One side of each winding goes to ground. One side the, you know, the higher winding, because your impedance is higher on your crystal filter, the higher winding count goes then to one side is to your input, or your input and output of your crystal filter. The other winding, the other end goes to the connectors. So basically your signal goes through one winding to ground for the transformer, the transformer does what it does and converts it onto the other winding, which then gets shipped out or in, depending on how you're looking at it. So that's what it did. Pretty straightforward. I think you can see quite a few windings on for such a small core, but hopefully yours will come out with a little less, and you can get maybe 5, 8 windings to 12. But you do what you need to do to get the impedance you need. So anyway, very, very happy. You can see very flat pass band. Bandwidth is right on the money, and you can see quite steep skirts. In fact, we're looking here, we're on a 20 kilohertz, so each one of these is 2 kilohertz, and you can see from the center of my frequency, when you hit 2 kilohertz, you're down from the center of the frequency. When you hit 2 kilohertz over, you're about 65 dB down. It drops off pretty quick. So I'm very happy with it, very happy. The next thing I'm gonna do is take this proto board after I've moved everything over to the permanent circuit board, and I'm gonna repopulate it. I'm going to repopulate it, and I'm going to work to try to come up with about a 500 hertz filter for our CW. That'll be next, and these will be in different videos. Thanks a lot for watching. I hope it's been useful, and I'll see you on the next video. And if you don't mind, take a moment if you haven't, and subscribe and like. It helps me out a lot. It doesn't cost you anything. If later you don't like the channel, you can unsubscribe. So thanks a lot. See you in the next video.